Good day, G10. One quarter down. I know it's been a good start as we covered topics about sequences and patterns. Now, I'm hoping that you can still recall from our introduction the next part of our lesson on Mathematics 10A. For the second quarter, we will be discussing geometry, and the main focus is circles. To start with, we will have Lesson 5, which is about chords, arcs, central angles, and inscribed angles. Our target for these lessons are derive inductively the relations among chords, arcs, central angles, and inscribed angles, and prove theorems related to chords, arcs, central angles, and inscribed angles. I know you've been missing watching your favorite movie with your family or friend. So consider this scenario as you get a chance to see another one. The chairs of a movie house are arranged consecutively like an arc of a circle. Suppose your favorite seat is at point C because you like the viewing angle to the screen between points A and B. If the seat at C is already occupied, then you will be forced to pick another seat, which is D. Will there be a difference between the viewing angle from your favorite seat and your newly selected seat? Why is that so? Think of this question as we go over with our topic for today. But before that, let us start first with the definition of terms needed for us to understand the topic. The set of all points having the same distance from a fixed point is called a circle. The fixed point is called the center, which is also used to name the circle. On the figure, we have circle A. The distance from point B to A is equal to the distance of point C to point A. Radius. It is a segment having as its endpoints the center and a point on the circle. On the figure, B, C, D, and E are points on the circle, and A is the center. With those given points, we can identify three radii of circle A, which are segment AB, segment AC, and segment AD. Chords. A chord is a segment whose endpoints lie on the circle. Using again the figure, we can identify the chords, which are segment AD, segment BD, and segment CD. Diameter. It is a chord that passes through the center of the circle. In a circle, diameters are the longest chord. It has a length twice that of the radius. On the figure, we have segment BD as the diameter of circle A. Central angle. It is an angle whose vertex is the center of the circle. Its rays contains radii of the circle. Angle BAC containing segments AB and segment AC, and angle CAD containing segments AC and segment AD are the central angles of circle A. Inscribed angle. It is an angle whose vertex is on the circle and whose rays contain chords of the circle. Chords ED, BD, and CD formed three inscribed angles, which are angle EDB, angle BDC, and angle EDC. Arc. It is a portion of the circle. It can be named either clockwise or counterclockwise. With points B, C, D, and E on circle A, we can name some example of arcs, which are arc BC, arc CD, arc DE, and arc EB. There are three types of arcs: semicircle, minor arc, and major arc. Let us differentiate those three. Let's start with semicircle. It is an arc that consists of the endpoints of diameter and all the points of the circle that lies on one side of the diameter. Its measure is 180 degrees. A semicircle is named using three distinct points, two of which are the endpoints and an included point, giving us the idea that we can name two semicircles, which are arc BCD and arc BED. Another type of arc is the minor arc. It is an arc that is smaller than a semicircle. Its measure is less than 180 degrees. On the figure, we can name 4 minor arcs, which are arc BC, arc CD, arc DE, and arc EB. The last type of arc is the major arc. It is an arc that is bigger than a semicircle. Its measure is greater than 180 degrees, which is also named using 3 letters. On the figure, we may say that arc CBD or arc CED is an example of a major arc of circle A. Point C and point D are the endpoints of this arc, wherein we can choose between point B and point E for the included point in naming this arc. Congruent circles. Those are circles with congruent radii. On the figure, if segment AB is congruent to segment CD, then we may say that circle B is congruent to circle D. Congruent arcs. There are 2 conditions for us to consider that the arcs are congruent. The first one, they belong to the same circle or 2 congruent circles. In reference to circle Q, we have arc CD and arc EF that are congruent, wherein they both measures 110 degrees. In reference again to circle Q and another circle P, we may say that arc BA is congruent to arc EF if and only if circle P is congruent to circle Q. The second condition is that their central angles must be congruent. In reference with circle Q, if angle CQD is congruent to angle EQF, then we may say that arc CD is congruent to arc EF. The second condition is that their central angles must be congruent. In reference with circle Q, if angle CQD is congruent to angle EQF, then we may say that arc CD is congruent to arc EF. Another case is that given circle P congruent to circle Q, we may say that arc BA is congruent to arc EF since angle BPA is congruent to angle EQF. Since we're through defining the important terms, we will now be moving on to the next part wherein we will be discussing the theorems and relationship among each line segments, angles, and arcs relative to circles. A central angle separates a circle into arcs. In the figure, angle GFH separates circle F into 2 arcs, arc GH and arc HIG. For every arc on a circle, there corresponds exactly 1 central angle. Arc GH corresponds to angle GFH since the given angle contains on its ray the endpoints of the arc. Conversely, we can say that arc GH is an intercepted arc of angle GFH. Central angle intercepted arc postulate. It states that the degree measure of a central angle is equal to the degree measure of its intercepted arc. Given the measure of angle GFH as 40 degrees, we can say that the measure of arc GH is also 40 degrees. Another postulate regarding the arcs of a circle is the arc addition postulate. It states that the measure of an arc formed by 2 adjacent arcs is the sum of the measures of the 2 arcs. On the figure, arc CA is adjacent to arc AB. Adding the measures of those 2 arcs, we may get the measure of arc CAB. Another example is that arc CB adjacent to arc AB. Let us take this example. Given circle C with points A, B, and D, and the indicated measures of its arcs, what is the value of x? Given the measures of arc AB, arc BD, and arc DA, we can use those measures in solving for the unknown, which is x. Applying the arc addition postulate and the idea of the complete revolution of a circle, which is 360 degrees, we may have the working equation measure of arc AB plus the measure of arc BD plus the measure of arc DA is equal to 360. Substituting the given, we have 4x plus 15 as the measure of arc AB, 6x plus 3 as the measure of arc BD, and 92 as the measure of arc DA. We may isolate the unknown on one side of the equation and then simplify, giving us 4x plus 6x is equal to 360 minus 92 minus 3 minus 15. By simplifying, we have 10x is equal to 250. And then solving further for x, we have x is equal to 25. To check if our answer is correct, just substitute the obtained value of x, which is 25, on our working equation, giving us the measure of arc AB, which is equal to 115, and the measure of arc BD, which is equal to 150 degrees. And then adding 115 as measure of arc AB and 153 as measure of arc BD, and also the measure of arc DA, which is 92, we may obtain the value, which is 360, meaning to say x is equal to 25 is correct.